Let me click on record to the cloud. That should be good. All right, so this again is one of these sort of broad maps. When we've looked at a similar map when we talked about deforestation, areas that have been impacted by human beings. This is a map of soil degradation. Soil degradation includes several things, right? The most significant aspect of soil degradation by far is soil erosion, where we lose soil that is in effect irreplaceable from a particular location. So, you know, something like 2/3, maybe more, of everything that we talk about in terms of soils being degraded really deals with erosion, right? There are other aspects to soil degradation. There's physical degradation, so there's compaction, which is problematic because that reduces infiltration, increases runoff, and increases erosion. There's chemical degradation, the structural and chemical degradation of the soils. So it is a multi-layered issue, but for the most part, we're talking about the removal and the loss of soils. And so when you look at this map, and what's beyond the scope of this course is to go into the details of what we really mean by severely eroded, moderately eroded, and so on. But there are three or four actually colors here on this map, and for our purposes here, just think of the red as being areas of severely degraded soils, very high rates of soil erosion, very high either compaction or chemical degradation, right? And then moving through to high, moderate, and low. And as you move from the red to the green there, incidentally, it becomes increasingly more difficult and sometimes just impossible to remediate those soils and return them to productivity, right? Soil erosion, when the soil is lost, it's lost, and it's very difficult and expensive and impractical for farmers to then start dragging soil back up from a particular region and returning it to a field or whatever the case may be. So when we look at this map, right, we begin to hone in on certain areas. Okay, we come back to this area here. I've circled this area many times in this course, right? So Southeast Asia have very highly degraded soils. Parts of Africa, for example, certainly Southern Africa, look at Madagascar again, and even the United States, right? The US has areas that are moderately to highly degraded. So soil erosion, soil degradation is a global issue. And as I made a comment, I think yesterday before we started this, it's not one that's just like bursting at the seams in terms of being right at the forefront of the media's attention. Right? It tends to be in the background because as I think I also commented, and I'll try and explain how that works. It's one of these issues that really nickels and dimes you to death. Eventually you run out of this very important resource. So when we talk about degradation, there are all sorts of various grades, and I'm just going to give you a graphical look at different types of soil degradation. So this is considered light soil degradation. This is a photograph I took in the United Kingdom on a winter's morning of a corner of an agricultural field. And you can see here there's some snow that's just receding. So this is a snow melt event, and runoff has come down, surface runoff has come down the slope and carved out these little channels. We call those little channels rills, incidentally, R-I-L-L-S. Okay, here's another little set of rills, and the sediment is being transported and deposited in the bottom part of this agricultural field, right? Again, there are some quantifiable, measurable ways to document and define what light erosion is, but this is recoverable, right? This is not catastrophic erosion being removed from a particular location. What are the processes involved in soil degradation and soil erosion? So I'll just touch on these really briefly here, everybody. The first one is raindrops, right? And we technically lump this all under a process called rain splash detachment. The power of impacting rain is, I think, dramatically underappreciated. Perhaps that's the best way to phrase that. Rainfall has a very high kinetic energy, okay? and dislodges huge amounts of material. This photograph on the left here, I had a student when I was teaching in North Carolina, and I was interested in just how susceptible the soils, and in particular soils under tobacco, was to erosion. So this is a tobacco plant over here on the right, and it shows the amount of sand that had been splashed onto this leaf. And this poor unsuspecting student of mine went around in these fields for 6 months after storm events, washing sand off these leaves to calculate how much soil had been dislodged and transported. Rain splash detachment is an especially efficient process in soil erosion. But then once runoff becomes concentrated and starts carving out these little rills, rills begin to grow into larger rills, and eventually that erosion ends up looking like this in many parts of the world. So these aren't technically rills. This is technically a gully, G-U-L-L-Y, and you can see it's really large, huge amounts of material. This is taken in southern Spain. A broad way of thinking of the difference between a rill and a gully is simply that a gully cannot be removed by machinery, by agricultural equipment. So you wouldn't find a tractor easily coming in here and redistributing sediment. So the point simply is that there's the scale of soil degradation or soil erosion from minor or light through to significant, right? Vast amounts of material can be transported and removed. The other important concept I just wanted to get out there, everyone, is like climate change, where we have a natural change in climates, and then we have this human footprint on top of it. And like extinction, we've got natural background extinction versus accelerated extinction. The same concept holds true in terms of erosion, right? So this is massive widespread soil degradation, but this is natural. Humans play no role in this, right? This is Zion National Park up in Utah, and this is what we call geologic erosion, right? The natural wearing away of continents by wind and water and ice. What we're talking about here over short time periods, not geologic time periods, is accelerated erosion, right? Erosion, the removal and the transport and the degradation of soils by human activity, whether it's commercial scale agricultural, subsistence agricultural, whatever the case may be. So there are three broad land uses here that lead to widespread global degradation of soil, right? I've just summarized these here. One is overgrazing. You can see, everyone, how this is linked to something like deforestation, right? So overgrazing, concentrated overgrazing by cattle and sheep, deforestation, right? And other agricultural activities. Those three are the big three, and you probably would have been able to argue that prior to even seeing a slide by this. I'm not going to ask you what these percentages are in the exam, but just be aware that these three land use, land change activities, agriculture, deforestation, and pasture, lead to significant degradation of soil. So what we've seen here in the Anthropocene, however we define that, is large-scale conversion of the land surface, right? This is a photograph taken in China of rice paddies on terracing. You can see a really novel way of farming over fairly steep and marginal lands. Any comments on that? Any questions on the major drivers of erosion? All good. Okay. Next question I want to address, and this is where we will come to this little calculation. So how much soil are we losing, right? Both here in the United States and around the world. And I guess the ultimate question is, do we have a soil erosion problem, right? Are we losing soils at rates that are non-sustainable? Are we running out of topsoil? Are we running out of this medium in which we grow things? So right at the outset, folks, I showed you this slide, right, in our very first meeting, when I talked about some of the big issues that we're going to tackle here. And this is one of them. So I just wanted to remind you that an area the size of China and India combined has been severely degraded in the last 60 years, to the point that cannot be remediated, right? You cannot bring back kind of re-stimulate these soils, whether you're trying to introduce organic material or just put down more topsoil, right? You can go to your local Home Depot and buy little bits of topsoil for your indoor pot plants. But when we're trying to replenish soils in agricultural regions, it's just not practical, possible to do. Right, so how much soil are we losing? So does everybody recognize this satellite image, what we're looking at here? This is a place that's pretty close to home, right? I always like to start with this one. Here is New Orleans, the great city of New Orleans. And this, of course, is the Mississippi Delta, okay? And this is a satellite image taken of the Louisiana and Texas coast following a number of large storm events. And you can see these sediment plumes, right? You see them all along the coast here. You see them down here in Houston. You see it coming out of Trinity Bay here, and also down on the right here. So we've got a series of widespread rain events across the southeast of the United States, and large amounts of sediment flowing down our rivers and into the ocean, right? This sediment here that you see flowing into the Gulf is largely our agricultural topsoil. And now remember, everybody, erosion and the transports of sediments to river channels, and then the movement of that sediment along river channels ultimately into the oceans is a natural process, but we are accelerating that, right? We're accelerating the transfer of sediments into our watercourses, and that represents a resource, that represents this physical resource that we need, right? So how much soil are we losing? So one comment I'd like to make is it's really quite difficult to estimate exactly, right, how much soil we're losing. If we think back to one of those early concepts we talked about, everybody, of accuracy and precision, it's very hard to get a real accurate and precise measurement of how much soil. Think about that, how we go across the Midwest, for example, and try and estimate that. There's lots of ways we can do that. There's soil erosion models, there's real measurements. This is an area that I've been involved in over 20 years of research and looking at soil degradation and soil erosion. But we can come up with some good estimates verified by on-the-ground measurements of how much soil is being transported. So there's one thing I also want to emphasize and stress here, and that is you may have a series of agricultural fields here. So let's say where I'm circling and coloring in here is a series of cropland areas, right? We may have soils being eroded off that agricultural land, okay? So we would have what is known as an on-site rate of erosion, how much soil is being removed on-site at a particular location, okay? Versus how much is being delivered off-site, right? How much is actually being transported to either a lake, reservoir, stream, or the ultimate sink, which is the ocean, right? So when we look at the Mississippi, just as an example, so the Mississippi is the river that transports the most sediment in the United States to the oceans. We are transporting, on average, about 150 million tons of sediment each year down the Mississippi and into the Gulf of Mexico. It used to be much higher than that, but as we've put so many dams and reservoirs and weirs and so on along our rivers, a lot of that sediment gets trapped before it actually makes it out into the oceans. But nonetheless, we're still transporting about 150 million tons of sediment every year into the Gulf of Mexico, just along the Mississippi alone. If that number has no meaning, and it probably doesn't have any meaning to you, think about this. That would be the equivalent of taking a Ford F-150, just your regular Ford F-150 filled with sediment, right? And driving past your feet every 8 seconds, right, for a year. That's how much sediment is coming down the Mississippi. So it may not sound like a lot, or 150 million tons may sound like a lot. It is, right? It's about a Ford truck every 8 seconds being dumped into the Gulf of Mexico. So that's pretty extraordinary amount of soil being lost. Okay, a graph for you, right? So is the news good or not when it comes to erosion on US crops? So here's one of these diagrams that has a couple of axes. So let me just slow down here and explain what we're looking at here. This is an important diagram, everybody. So every 5 years, the US Department of Agriculture, in association with a number of other agencies, does an assessment of how much soil is being lost in the US. Okay, we didn't have anything in 27. We're still waiting. We've basically got a decade here where there hasn't been any reporting of soil erosion rates in the US. But we do have some indication of what's happened over the last 30 years or so, something like that, from the USDA. So what we're looking at here on the left axis is on-site, so I need to just emphasize that, on-site erosion in how many billions of tons per year, right? So that's 1 billion tons, 2 billion tons, 3 billion tons. And that relates to these vertical columns. And the columns have been split out into erosion by wind, that's the top one, and erosion by water, okay? That distinction is not necessarily critical in and of itself, but I just wanted to give you a feel that, and just to remind you, and to remind myself, I suppose, that it's sediment transport by both wind and water. So these columns refer to the left-hand side here, the left-hand axis, and this number here and the red curve relates to the right-hand axis. That is the erosion rate in how many tons per hectare per year, right? So this is on-site erosion in terms of total billion tons, and then expressed as a rate per hectare of cropland, right? And remember, folks, a hectare is 100 meters by 100 meters, or 2 football fields minus the end zones, okay? So what do you take away from this? What can you see? Well, you can see that in the 1980s, we were losing about 3 billion tons of soil per year and upwards of 17 tons per hectare. And for, you know, this decade here, we're pretty static down here at about 1.5-ish billion tons per year, a little bit more than that, or about 11, right, tons per hectare per year. Can everybody see that? So from 1982 to 2012, we've actually seen quite a significant decrease in the rate of soil erosion and soil degradation in the US, right? And at the end this morning, I'm going to talk a little bit about why that may be. What are the things, what's been going on to reduce erosion rates in the US? So that's good news, right? There's a good news story here, and that is that we have reduced by about 50% the amount of on-site soil erosion in the US since 1982. So that's good, okay? There are parts of the world where it's far more acute. Okay, erosion is a much more significant issue. It's a significant issue here in the US. We're ultimately still losing 1.5 billion tons of soil off our fields, our agricultural fields, but it's more so in other parts of the world, right? So when we look at, whoops, let me just clear that out. I've got the wrong button on here. Okay, so when we look at just water erosion, let me go back a second. If we're just comparing the blues, right, water erosion here in the US, I've tried to sort of sum this up in this little infographic type thing here, okay? Natural erosion, this background rate of erosion, the average rate of soil erosion under natural conditions should be less than about 2, and this unit here, everybody, that's the same as tons, megagrams, should be about 2 tons per hectare per year, right? That's normal natural background rates of erosion. Okay. In the US, we are losing about 6.7 to 7 tons per year, but in other parts of the world, China, for example, the average erosion rates are about 15, right? So the take home of all of this is that in other parts of the world, they are losing soils at rates that exceed twice what we're losing here in the US, okay? And the US is still pretty significant. And that's why when we have a summary diagram that says we've lost an area the size of China and India combined, is because soil erosion has been such an acute problem around the world. Does that make sense? Okay, now let's keep going here, and we've got to ask the question before I get to the calculation here, everybody. We need to ask the question, when we look at that diagram from 1982, and it goes from 3 billion tons and it comes down here to 1.5 billion tons, that erosion rate is about 11.5 tons per hectare every year, right? That's the current average rate of erosion on US topsoil. So let's just round that up to 12, okay? Let's say 12 tons per hectare represents the current average rate of soil erosion in the US. And that's a number that would be good to remember, right? 12 tons per hectare per year. That's how much we're losing. What does that mean, right? How much soil is that? And is that sustainable in the long run? Okay, so here's my way of trying to make that number a bit more meaningful. So let's say this diagram here that I've done represents 1 hectare of soil, okay? And remember, a hectare, as I've just said, is 100 meters by 100 meters, or 2 US football fields minus the end zones sitting side by side, okay? I'm leading to something here that's going to be on this final exam as a calculation, so hang in there, everybody. So if you were to scrape 12 tons off 1 hectare, so if you came along and you scraped off a surface layer that ended up weighing 12 tons, and that would fit into, you know, a pretty large sized dump truck like I've got here, more or less, okay? That would represent a vertical loss of 0.04 inches of soil. So that's the important number here, right? So 12 tons per hectare per year, which represents the average rate of soil loss on US croplands, equates to a vertical depth of 0.04 inches. Does that make sense? Right, so if you take a ruler here, now I know you folks are inches people, but if you take a ruler, right, so that's just a little inch down at the bottom there, we're talking about 0.04 of an inch. It's a minuscule amount of soil coming off that field, and that represents 12 tons if you scrape that off the entire field. Is everybody with me? Make sense? Right, so I'm trying to give you a linear vertical measurement feel for what 12 tons per hectare looks like, okay? So the next question is, can we sustain that, right? Is that a sustainable rate of soil loss in the United States? Okay, well, the question is, what is sustainable soil loss? What does that actually mean? So we have this term here called tolerable erosion, okay? The T value, tolerable soil erosion. And not every soil in the world has been assessed, but all soils in the US have actually been assessed and are given a T value, a tolerable soil loss value. Now there's 2 definitions here, everybody, and I want to just read these definitions out because there is a fairly significant nuance here to both these definitions. They're both correct, right? So what do we mean by tolerable erosion? So the first one is maximum soil erosion loss that is offset by the theoretical maximum rate of soil development. In other words, are you losing soil, right, at a rate that is less than the rate at which soil is being formed? Okay, does that make sense? So you're looking at the balance between soil loss and soil formation. This, incidentally, everybody, is really hard to quantify, okay, because we know that soil development is slow, right? The second definition is, and I'll read it, the maximum average annual soil loss that will allow continuous cropping and maintain soil productivity without requiring additional management inputs. Okay, and I'm just going to highlight that in red. Without requiring additional management inputs. What do you think we mean by that, additional management inputs? What does that conjure up? Do you think? Why is that even in there? What do we mean by additional management inputs?
Does it mean that it would be the like the natural reproducing of soil instead of us having to manually bring it in?
Yeah, okay. That's part of it. Let's come back to maintaining soil productivity.
So without having to enhance the soil, chemically, we refer to naturally, bounce back.
Right. And what do we normally add to soil to increase its productivity?
Carbon.
Yeah, fertilizers, right? So we dump stuff onto the soil and incorporate it into the soil to try and maintain and or increase the productivity of that soil. Right? So what this definition is saying is how much soil can you afford to lose, right? That will allow you to maintain your productivity and your crop yields without starting to, as Matt said, either add more stuff to the soil, physically add to the soil, add fertilizers to the soil, and so on, right? So there's two definitions there. They're both related to one another, but one relates to soil loss versus soil development. The other is soil loss versus management input. And it turns out in the United States, right, for US soils, the T value ranges from 2 tons per hectare to 11 tons per hectare per year, okay? Or if you prefer acres, just to keep you happy, 1 to 5 tons per acre per year. So it's about 2 to 11 tons per hectare per year. That is the range of T values in the US. Why is it not one number? Oh, there's a nice exam question. Why is the T value not a single number? Why is it not 3.5 tons per hectare for every soil in the US? Do you think?
Does that have to do with the topography of different regions in the world?
Okay, keep going.
That in certain places, the soil is more fertile overall, but in other places, it's very, the climate dictates it being very non-usable.
Right, okay, and all of that, thanks, Matt, and all of that is tied up in a term or a concept that is basically how erodible is the soil, right? Not all soils are equal, okay? Soils have different erodibilities depending on the slope that they're on. So you're right, what is the topography? Depending on the clay content, depending on the organic matter content, depending on the chemistry of the soil, right? Depending on the climate, how much rainfall is driving that. So soils have a certain erodibility, right? Some are pretty stable and not very erodible. Others are highly erodible, okay? So the T value is a range, and it depends on how erodible the soils are. It also depends on how thick those soils are, right? If you're a farmer and you have deep, thick soils that are, 3 to 4 feet thick, then you could probably afford to lose up on the upper limit here, right? But if you're a farmer that is in West Texas and your soils are thin and there are residual soils on, bedrock that is in parent material of 3 to 5 inches thick, then you're probably very likely down at the 2s, okay? So the T value determines whether your soil is sustainable or not, okay? All good? Okay, so here is the example. Here's the calculation on what I'm going to expect you to do. And so here's how I'm going to phrase this in the exam, everybody. I am going to ask you, I'm going to give you a scenario, and I'm going to ask you whether you think this farmer has a soil degradation problem or not, right? That's the construct here. Does this farmer have a soil degradation problem or not? Okay. Let me just do something here. Right. Yep, that works out. Just double checking the calculation. Okay. So here's how this works. All right. Here's one of my grad students standing in a nice little erosion feature in England. And the first question that I want to address here is, so what is the rate of soil formation, right? So that's really hard to know, okay? Because remember that first definition of the T value is the rate of soil loss relative to the theoretical rate of soil formation. So there's been a lot of experimental work done in labs and also dating soils. So to be able to look at how thick a soil is, to be able to date that soil using various techniques, which we don't have to get into, that's well beyond the scope of the course. But here is, I think, a pretty common sense average, and this is an average, is that it normally takes on average about 500 years to build up 1 inch of topsoil, right? So let's just stop there. Some parts, soil formation is very slow. So if you're in the desert Southwest, right, and you don't have much rainfall, and you don't have much nutrient cycling, and your parent materials are perhaps thin, it may take much longer to build up an inch of topsoil, right? If you're in an area that is in optimal climate and you've got lots of, infiltration going on, it may take less time. So we do use an average here of about 500 years to build an inch of topsoil, right? So every 500 years, you're building an inch. In other words, you are building 0.002 inches per year, 1/500th of an inch each year. 1 divided by 500 gives you 0.002. Does that make sense to everybody? Pretty simple. 1 divided by 500, okay? So on average, we're building soil at a rate of about 0.002 inches per year. How much soil do you need? Well, that depends on the crop, but generally you need about 6 inches of soil to be considered viable. Some plant in less, some plant in more. So you can see immediately that, we're talking on the order of thousands of years to build up soils that are agriculturally workable, okay? So maybe 3,000 years to build up 6 inches of soil. So if we are forming soil here at a rate of 0.002 inches per year, right? Or every 500 years to build up an inch, then what does the rate of soil loss look like? Okay, so here's the key, right? If the current rates of soil loss in the US are 12 tons per hectare per year, right? 12 tons per hectare per year. Remember I said on that previous diagram that 12 tons per hectare per year equates to 0.04 inches, right? That's 0.04 inches of soil being lost every year. Everybody with me? Okay. Or about 1/25th of an inch. Okay. 1 divided by 25 equals 0.04. If that makes sense. Right, or 1 divided by 0.04 equals 25. So we are losing soil on average in the US at about 0.04 inches per year. We're forming soil at 0.002 inches per year. The question would be, is there a soil erosion problem here? Is there a soil erosion problem? Well, absolutely there is, right? And if I was to ask you, and this is going to be how it's phrased in the exam, guys, on Thursday, at what rate are we losing soil relative to soils being formed, right? Does this farmer have a soil erosion problem? And if so, how many times faster is soil being lost than formed? How would you answer that? Do you think? All the information that you need is on the slide here. It takes 500 years to form an inch of soil. It takes 25 years to lose an inch of soil. We're building soil at 0.002 inches per year. We're losing soil at 0.04 inches per year. Is there a soil erosion problem, everybody?
Yes.
Yes. Okay. How many times faster are we losing soil than soil's being formed here? How would I calculate that?
20 times.
Exactly. 20 times, right? 20 times. Just take 500 divided by 25, right? Or take 0.04 divided by 0.002. That's the soil calculation, okay? Please, folks, don't overthink this in the exam. Sometimes I get pages and pages of calculus. You're just looking at the rate of formation and the rate of soil loss, right? Does that make sense? Cool. All right. I'll give you some different numbers. And I have to give you those numbers, right? I have to tell you what the vertical rate of soil loss is and what the rate of soil formation is. And it's a simple, straightforward calculation. But I think it's important because, and the reason why I do this, not just to make you do a calculation for the sake of doing a calculation, is for you to just appreciate that this average rate of soil loss that we currently have, 12 tons per hectare, right, is not sustainable, okay? Because the T values in the US are 2 to 11, right? In other words, the current rate of soil loss in the US is above the range of T value. Now, that doesn't mean that every place in the US is losing soil catastrophically, right? Not at all. But here's what it does mean, right? When you look at the United States, and if you were to just look at where soils are being lost at 1.5 times the tolerable rate and more than twice the tolerable rate, this is the map that you get, okay? These are the most susceptible soils in the US in terms of erosion. So what do you see? What jumps out at you when you look at this map? This is the sensitivity map, if you like, of soil erosion in the US.
The farming in the Midwest and the tobacco plants on the East Coast are severely limiting the soil.
Yeah, nice, right? So what does this look like? All of this. Well, that's soil that's coming off our agricultural heartland, right? This is the 150 million tons of soil ending up in the Gulf of Mexico. Erosion in the Midwest, even though it's been dramatically reduced from 3 to 1.5 billion tons, right, since 1982, we are still losing soils at a rate that is 1.5 to 2 times the tolerable rate, right? You know, this is not fake news. This is straightforward sediment and fluid dynamics, and we'd better do something about it. And we are, and it's not that the Midwest is running out of soil anytime soon, because we've got soils that are pretty deep there, but they're not going to last 200 years, that's for sure. What's going on here? Look at the great state of Texas. And in particular, this part of the world, which we're going to come back and refer to in the next lecture. Anybody from West Texas here in the class? I hope there is.
Isn't there a lot more farming in West Texas?
Say that again, Claire?
Isn't there a lot more farming in West Texas?
Yeah, right. Huge agriculture over here. And anybody know what happened here in the 1930s? Right, probably. Mary Morgan?
Dust bowls.
Yeah, the Dust Bowl, right? So the Dust Bowl is when the Great Plow Under occurred, right? And we take all those grasslands in Kansas, Oklahoma, and West Texas, and we plow them under, and then we go through a drought and everything blows away. Okay, I once did a drive from LA to Dallas, and I came across I-10, and I drove through El Paso, and I came up through West Texas, and yeah, it was very dusty, and there was lots of soil in the air. There are large parts that are susceptible to erosion. So it's not like the continental United States is sliding into the ocean, but it's this insidious background 0.04 inches every year. That just doesn't sound very dramatic, but eventually it catches up to you, and you run out of this resource, right? This critical resource that you need. What can be done and what is being done? Well, here's the good news, okay, is that since the late 1970s and really the early 1980s, the US Department of Agriculture put in place a series of what we call BMPs. Okay, that's a little acronym that just simply stands for Best Management Practices. Okay, some of them are engineering structures, right, to hold back soils, but most of them are not. Most of them involve manipulation of vegetation and the way in which we farm. Right, best management practices. We are looking at the slide without me giving anything away. We're looking at a best management practice in action on this image here. What do you think it is with these happy grass-fed cows?
Limiting where they can graze at any given time.
Bingo. Yeah, nice, Mary Morgan. Right, so here the cows are kept on this side of the fence. This is known as rotational grazing. And here, the alfalfa grass is allowed to grow and replenish. And then they will shortly move these cows over here, and they will let this try and regenerate, right? So that's called rotational grazing. It's a very simple, straightforward, common sense approach to not letting your cows overgraze everything and destroy the surface, right? Because that grass protects and binds the soil. Okay, here's another series of best management practices. Here are strawberry fields in California. Take a moment to look at this. I can see, one's going to seem obvious, and I'll explain that in a second, but I can see at least two best management practices going on here. What do you see? Strawberry fields. Just incidentally here, I'll take one off the table. The plastic here is not protecting the soil from erosion. The strawberries are very sensitive to moisture, so they are planted on these little ridges and covered here to keep the moisture in. So there's very strong moisture control on strawberries. So don't worry about the plastic. What else do you see here that you think might be a best management practice? Anything jump out? Look at those lovely strawberries all sitting on the ground. What do you notice about those rows of strawberries in this image, everyone?
Yeah, I don't know what it's supposed to look like, but it looks like it's pretty sandy or something.
Yeah, it is a sandy soil, actually. Okay, but that's not the BMP. What do you notice about the rows here? Why aren't the strawberry fields, why aren't these rows of strawberries oriented like that? Why aren't the green lines doing that?
Sun?
Claire?
Does it have to do with the sun and like where it would hit?
No, not the sun, but keep thinking.
Is it the natural like runoff, or like the natural way the water can flow out?
Yep, this is a runoff control, right? These contours here, these rows of strawberries are following the contour of the slope, right? And then coming up like this, okay? See that? Come down here, and then they come up like this, right? So this is a best management practice called contour plowing. Again, simple and straightforward. And yet when I was doing my PhD work in England, every single farmer went up and down the slope, and up and down the slope, because that's just what they did. And then the rain fell, and it was channeled straight down the slope, right? So this is contour plowing, which almost everybody uses now. In other words, as runoff begins to collect, if it starts raining and we're getting runoff collecting down the slope, it's got these ridges. It's being held back all the way down that slope. It reduces the velocity of the flow, therefore it reduces soil erosion dramatically. Now, at some point, right, you've got to get the water off the slope. So we can see some waterways coming down the center here. But what do you notice about the waterways? They are, well, they're covered in grass, right? So this is now planting grass strips to increase the potential for sediment and material to fall out of suspension as that runoff moves down slope. Pretty simple and straightforward, right? Here's another example. These are two aerial images from Iowa showing something quite similar, right? So here's contour plowing. So this is all corn following the contours, okay? So that's reducing runoff. Now, in addition to contour plowing, we've got these grass strips. So this is also known as strip cropping. So we've got contour plowing and strip cropping superimposed upon one another. Okay, in other words, you're going to have water collecting and trying to get out of that field somehow, but instead of just having these row crops, plant these alfalfa strips that also reduces velocity and traps sediment along the way. And then when you do have to evacuate water, these are all grass strips right out of there. And you see the same thing on the right-hand side here. So all of these are BMPs. And then finally, here's the last one, which is a farmer that is planting corn again in Iowa. So you can see the contour plowing here, right? So these are the ridges of the corn following the contours. And what's going on here is another best management practice, and this is called no tillage, right? No till. Sometimes it's minimum till, but this is actually no till. What is that? The farmers come on in here, harvested the crop, right? Cut it all down and harvested the crop, left all of the previous year's grass and stubble on the surface. So you're increasing the organic matter content. Matt, you mentioned this, you're increasing the carbon content. You're not plowing up the soil, so you're not disturbing it. And then you're planting next year's seed directly in here, right? That has also dramatically reduced erosion in the Midwest. So there are a series of these best management practices that are practiced here, not just in the US, but around the world. All right, let me stop there and see if there are any comments or questions on soils. So that's just the US perspective, right? And the kind of parting point is in other countries, it is a catastrophic issue, right? All good. Okay, let's, what do we do? A little early, it's 8:50. Let's take a 10-minute break and we will come back and move on to this magical stuff. We're going to look at the water crisis. So let's take a 10-minute and I'll pause the recording. Okay. All right, on to chapter 10, everybody. So this is a two-part session. We'll start with the first part here, introduce you to some concepts that relate to water supply. And then, as I said, tomorrow we're going to talk about water pollution, water quality for the first half, and then we'll wrap everything up. So that's where we're headed now in terms of the issue. The next one is kind of the often seen as maybe the greatest crisis of all, I suppose, and that is the ability to get access to fresh, potable, safe drinking water. I think it's something that perhaps we just take for granted here in the US, but again, many parts of the world, that's not the case. I can attest to this firsthand in several countries in Southern Africa where people spend literally hours a day, right, seeking out potable water. And yet, you know, when we need it, we turn on the faucet. So access to clean, safe water is still a concern globally and a major concern in many parts of the world. It's not just a question of where the rain is, right? This is another one of these generalized maps, and as you get into the darker blues here, you get higher rainfall. So as expected, we get lots of rain in the tropics where the tropical forests are, but there are some critical drought or hotspots, I suppose, if you think of water supply. One is clearly the desert Southwest, right here in the United States, which is facing some significant water issues. Obviously, if you're living in the Sahara, the Sahel region here, or the Middle East, okay. Southern Africa is another one for sure. My part of the world where there is considerable water shortages for most of the time. So there are parts of the world that have plenty of rainfall. There are other parts of the world that do not, right? So there is an immediate disparity between the haves and the have-nots in terms of access to rainfall. Sometimes there's just simply too much of it, right? So the next set of slides focuses on this region over here. So let's look at the Himalayas here, just as a case study in this. And this is the wettest place on Earth. This is a town in India called Cherrapunji. And Cherrapunji experiences catastrophic rainfall in the months of May, June, July, and August. Just look at these totals, right? In July, this town receives over 120 inches of rainfall, okay, in 1 month. Folks, in Fort Worth, we get 35, oh, my mouse is just frozen. Oh, that's a bit unfortunate. Give me 1 second. In Fort Worth, we get about 35 to 36 inches of rainfall a year. This part in India gets 120 just in that month. Let's see if that's working now. That looks like it's working a little better. Sorry about that. My mouse just went on the blink. There is an enormous seasonality to the rainfall in this part of the world, right? So here we are in January, February, March, okay? And here we are in October, November, and December. And these are the so-called monsoon months, right? When rainfall is much lower in this part of the world than in other parts. And so the access to rainfall is not the same wherever you are in the world. Oh boy, my mouse seems to have frozen again. This may be a little problematic. Maybe not. And this is the reason why Tirapudi is so wet, right? This is influenced by, okay, my mouse is going weird here. This is influenced by orographic rainfall, and that is rainfall that is enhanced by mountains, right? Now we talked a little bit about mountains in biodiversity, but what happens here is during the onset of the monsoon season, which is April and May, we have flow coming out of the Indian Ocean here, and it brings huge amounts of rainfall into the Indian subcontinent, okay? So it's not just a question of having too much rainfall. Very frequently, it's a question of having too little rainfall. I am going to have to take off this drawing thing because I'm just going to stick with not having the drawing thing. All right. Okay, so let's think about where the world's water is. Okay, again, not everybody has access to the same amount of water. So yeah, this is the water planet. 70% of the Earth's surface is covered by water. But when we just look at where our water is, the data on this slide, I'm going to use this just to make one point, right? And that point is that the amount of readily accessible fresh water is really small. So on the left here, this graphic from the USGS, which I love, is how the world would look if we took all of the world's water, including all of the water in the ocean, right, and put it into the sphere. That big blob on the left is all the water on our planet, right? This is a sphere. Now, there's a lot of water in there, but that's a sphere that has a diameter of about 830 miles, something like that, right? That represents all of the world's water, okay? The little blob next to that, sort of sitting over the Appalachians, Tennessee area, right? This, let me see if my mouse is working. This little one over here represents the liquid fresh water, and the tiny little dot here sitting over Atlanta, Georgia, represents fresh water in lakes and rivers. What does that look like from a percentage perspective, right? Let's take a look at the right-hand side. Let me see if my annotating pen will work here. So if we took all of the water on Earth, okay, we could see something like 2 to 2.5% is fresh water. The rest is water in oceans and lakes that is saline, salty water. So that's the first point, right? We've got all of this water on the planet. A very small percentage is fresh water, okay? Yeah, I've got a very sleepy mouse here. I'm going to give up on the annotating here, everybody. If we take that 2 to 2.5% of fresh water and blow it up on the bottom left here, so the bottom left represents all the fresh water on the planet, okay? You can see that the vast majority of the world's fresh water is tied up in ice and snow, right? 13% is liquid, okay? And then if we took the world's liquid water, the vast majority of that is in the ground. So all I'm getting to here is that when you look at the total resource on the planet that we call water, that just seems this endless supply, right? Most of it is saline, so 2% is fresh. Most of that fresh is frozen. 13% of that is liquid. Most of that liquid is deep in the ground, and a very tiny fraction is actually available to us in lakes, rivers, and streams, okay? So that's the point. And another way of trying to sort of portray this is if we were to take all of the world's water supply and represent that in these 26-gallon containers, the total amount of water on the planet, including all of the ocean's water, right? About 3/4 of that would be fresh water, so about 0.8 gallons would be the fresh water on the planet, but most of that would be frozen and most of that would be in groundwater. And the readily available fresh water that you and I think of as, turning on the faucet and getting into our lakes, reservoirs, and streams would be about a half a teaspoonful, just as a graphical representation, right? So I think that's a really important concept for people to appreciate, is that this is a finite resource, and that whilst it seems vast and that we're not going to run out of water anytime soon, I think nothing could be further from the truth. So any comments or thoughts or questions? Does that make sense, going between the water compartments, i.e. where our water is, and just a graphical representation of where that water is? Makes sense?
Do you think that as we continue and the population grows and grows, do you think we're going to incorporate more and more of the desalination of salt water?
Okay, so that's a great question, Matt. And so that relates to both the access of water for agriculture and domestic use, but also for power generation. I think the answer to that is yes. The problem is it's just so expensive at the moment, right? So there's desalination plants throughout the Middle East and the UAE. I've driven past a couple in the UAE. The question is, can we afford to do that? Can countries that don't have access to water afford to do that? I think it's inevitable that we're going to be desalinizing more and more water. Yeah, for sure. It's an expensive process. Okay, next term, aquifer, right? So what is an aquifer? Because I'm going to talk a little bit about aquifers here and our supply. The first point I wanted to make, right? Let me see if I can get my mouse going here again. Is so an aquifer is just an underground geologic unit that can store and transport water, right? That's the broad definition of an aquifer. An underground geologic unit that can store and transport water. And there are two major types of aquifers, right? That I've tried to draw on this diagram here. And I apologize, my mouse has just gone totally on the blink, so I'm going to have to sort of explain these slides as best as I can. So there are two types of aquifer. One is a confined aquifer, and you see that along the bottom here, right? And a confined aquifer is, let me just try and give you an example of this. So I'm holding up a book here, right, that has a cover on the top and a cover on the bottom, right? It's a hardcover book, okay? If the pages in the book here represent the geologic units that can store water, so if I was to force water into these pages, okay, that water would be under pressure, and the top is impermeable and the bottom is impermeable. That's a confined aquifer, right? Now it's going along horizontally here and it's going off the side of the screen horizontally here. But the point is that a confined aquifer is a geologic unit that has an impermeable or confining layer above and below it, right? In other words, water cannot penetrate vertically down through that confining unit. That confining unit is almost certainly some sort of clay or shale layer, right? And the rock inside that confined aquifer, in other words, all the pages in this book are completely saturated, right? So that's a confined aquifer. An unconfined aquifer would be like taking the confined aquifer and lifting the top layer over, right? In other words, the pages or the soil or the rock units are exposed at the surface, and water can get into them and recharge that aquifer from above, right? That's an unconfined aquifer. And that's the little inset that you see in this diagram here that I've pulled up and tried to draw here, right? When you look at this, the top layer of the unconfined aquifer is the water table. So if you went outside right now, if you can get to a garden or a field or something, and you were to drill a hole, eventually you would look down in that hole and you would see the water table, right? That's the top layer of the unconfined aquifer. So an unconfined aquifer is recharged by water that's infiltrating into the soil and gets directly into that aquifer itself. And so as you start recharging that, the water table rises, okay? But in a confined aquifer, that water is under pressure. Now, sometimes if you're lucky, and if it's under a pressure that's great enough, that water will rise up and spew out at the surface. And you've got what is known as a free-flowing artesian system, a free-flowing artesian well, right? But for the most part, what you have to do is you have to then put a pump down into the aquifer and pump the water out, right, of a confined aquifer. And the other point to make here, and then I'll just stop and see if there are any questions on this, is as you look to the left here, right, that confined aquifer has to be recharged somewhere. And so how is that confined aquifer recharged? The geologic units in it are exposed at the surface somewhere else. So that's known as the recharge zone. So yes, water will infiltrate here and then migrate down and remain under pressure. I hope that makes sense graphically. The challenge here, folks, is that the underlying geology, no matter where you are, is invariably very complicated, as this diagram tries to show. Right? At the end of the day, aquifers are geologic units that store and transmit water. Okay. Anybody in the class from San Antonio? Just as a matter of interest, do we have any Spurs fans in the class? No one. Okay. So here's an image of San Antonio, right? San Antonio gets almost all of its water from a geologic unit called the Edwards. It's the Edwards Aquifer. You may have heard of that, right? It's an underground geologic formation of limestones that can hold huge amounts of water. Okay? They're underneath San Antonio. Well, it depends. Some are as deep as 3,000 feet. Some are a little shallower. But it's the subsurface band of limestone which can transmit water. The rocks above it are younger. The rocks below it are older. So the blue here is the Edwards Aquifer. Okay? And it's a confined aquifer below San Antonio. But notice from this diagram that the blue rocks, the Edwards group of limestones, bands upwards and then becomes exposed at the surface here. And that's the recharge zone for the Edwards Aquifer, right? Where the blue is all exposed at the surface. And so I don't know if any of you have driven around there. I've driven around this part of the world, and you drive through Austin, and very often you'll go through an area and it'll say you're now entering the recharge zone, right, of the Edwards aquifer, the Edwards limestone. Does that make sense? And so the control or the management of these recharge zones is really important. It's critical for the management of these systems. In the DFW Metroplex, we get most of our water from surface sources, right, from surface reservoirs. So it depends on where you are as to where you get your water from. All right. So how much water are we using? Well, just like the census that's done on population and the census that's done on soil erosion and the counting of species, the US Geological Service does a water consumption census every 5 years. Okay, they haven't published the 2020 data yet. I think everything's been sort of held up and delayed by COVID. But anyway, we've got the 2015 data in terms of water use in the US, right? So here are some important numbers. And I'm not just going to throw out numbers for the sake of them, but this is the latest water use data in the US, right? So the most important one is the number in the center here in green. That's how much water we withdraw every day in the US, or at least we did over that 2010 to 2015 period. So this is a daily withdrawal average, okay, in million gallons per day. So 322,000 million gallons per day. That is the same as saying 322 billion gallons per day, right? The million gallons per day is the official unit. I don't know why they just don't report everything in billion, because it's a little cleaner. But I need to stick to the actual data that's reported, right? So in 2015, we were taking out 322 billion gallons of water every day. 87% of that, or 281 billion or 281,000 million gallons, was fresh water, and about 13% was saline water for various uses, including desalinization. There are some desalinization plants here in the US. Okay. So that's how much water we withdraw, 322 billion gallons. If we divide that by the population in 2015, we get how many gallons per capita, right? So that's the orange box. We are withdrawing 990 gallons of water per capita in the US per person. Now, there's a caveat here, everybody, and that is not how much water you are individually using, right? You would be in a gigantic swimming pool. That is the amount of water withdrawn per person, including power generation, including irrigation for all uses, right? So that's just taking the total amount of water that's being withdrawn, 322 billion, dividing it by the population in the US, right? That's 320 or so million. That gives you a per capita withdrawal. Does that make sense? Everybody okay with those two numbers, 322 and 990? 322 billion gallons, right? Okay, the good news is that that rate is down substantially from 2005. So in 2005, we withdrew over 400 billion gallons per day, right? 2010 was down 14% from 2005. So we were at about 355 billion gallons per day. And 2015 was down another 9%, okay? So we are down, you know, almost 20 to 25% improvement, if you like, less water being withdrawn. Okay, there's the 87% fresh water and the percentage of the fresh water that was surface. So most of our water withdrawal is surface withdrawal from reservoirs, 70%, 30% is from groundwater. Okay, so that's good news, right? That shows increased efficiency and reduced use. Be interesting to see what 2020 looks like, for sure. So where do we use our water? The two big ones, as you would imagine, are down at the bottom here, right? So these are the 2015 numbers, the 322 billion gallons per day, irrigation and thermoelectric power, like 42% and 37% for irrigation. Question: why do you think we are withdrawing 322 billion gallons per day as opposed to the 2005 400 billion gallons per day? Where has the savings been, do you think? Largely, not exclusively, but largely. Just as a guess. Why do you think we are withdrawing less water? Think about chapter 3. Anybody? Power generation, right? What about power generation? Why has power generation been such a big player in terms of reducing our water footprint? Do you think? Come on, folks. Something must have sunk in on our power generation. Why are we withdrawing essentially 20% less water than 10 years ago? We're still irrigating our fields. It's renewables, right? Largely renewable energy. If you're using so much water for coal-fired power plants, right? And coal has gone from 50% down to 20%, okay? We are using far less water in our coal-fired power plants. So that's been a huge saving in terms of water. Public supply is about 12%, right? Incidentally, domestic, that may be a little misleading. Domestic is off the public supply, so your own wells. But you can see when you look at usage across the US, it's really irrigation and thermal power that are the big drivers, okay, of water. I see the chat going here. Question: importing it? Yeah, Claire, we're not. No, we're self-sufficient in terms of water. But I'm glad you put that in the chat there, because there are many countries that do import, right?
Do we not import from Mexico at all?
Say again, I can't hear you.
For some reason, I thought we imported water somewhat from Mexico too.
Not that I'm aware of. Okay, and that may just be simply me not being aware of it. Has anybody else heard that? I know we tend to take all the water down the Colorado before it gets to Mexico. That's a whole nother issue.
Do we import some main resource from Mexico that we talked about, and I'm confusing it? Maybe
Oil, So significant
Okay.
oil imports. Yeah.
Thank you.
Yeah. No, all good. So we import oil. Yeah. Okay, here's another way to look at it. I always like to show this because some people are from out of town, from different states. So this shows water withdrawal in million gallons. So 20,000 million gallons is the same as 20 billion, right? And the map there shades it in to give you a regional perspective. So you look at the 4 thirstiest states here. Okay, California, well, that makes sense, right? About 28 billion gallons per day. The brown is groundwater, the blue is surface, right? So California gets more of its water from groundwater sources. Texas is the opposite, right? Texas is over 20 billion gallons per day. Almost 2/3 of that comes from surface water withdrawal, and a large 1/3 comes from groundwater, and I'll show you where in a second, where that is. Idaho? What? What's going on there? How can Idaho be the 3rd thirstiest state?
Those potatoes need water.
They sure do, right? Those cows do too, right? So agriculture in Idaho, big. Florida, as you would imagine, next one in, right? And what's really interesting, if you just look at, for example, Montana and Nebraska, so side by side, they use about the same amount of water. Nebraska gets almost all of its water from a particular, no, well, not almost all of its water, the majority of its water from a particular groundwater aquifer. Montana gets almost all of its water from surface, right? So the aquifer system, the groundwater aquifer system varies tremendously depending on where you are, right? Arkansas is another state that's heavily dependent on groundwater. So I just think just a kind of interesting, interesting map here. If we think of the US globally, right? Yeah, as expected, I suppose, maybe, we are the thirstiest state, right? So this is daily water consumption by country per capita. So there's the US in 2015. That's the 990 gallons per capita, okay? In 2015, again, that includes all water use, everybody. That is thermal power generation, agriculture, and so on. Canada's next one down. Big one there, of course, is agriculture again. But you can see the US is still the largest user of water. And here's another way to look at it. I always think this one's quite interesting. This is the average water use per person per day, excluding things like power generation and crop irrigation. So this is domestic use. The average American uses about 150 gallons of water per day, okay, on average. That's extraordinary. Where do you think, why is it so high? If we're taking out commercial scale agriculture and thermal power generation, that's a lot of water, okay, 150 gallons per person per day. That doesn't mean that you're sitting in the shower for 6 hours a day, although some do, but where do you think a large chunk of that red circle lies in terms of per capita use? There's this amazing thing driving around this part of the world, and you drive through neighborhoods and everybody has these beautiful green lawns, right? So that's watering our lawns in our houses. Accounts for a huge chunk of the American use, right? What is startling here to me, and again, these are some of the, the big users I've just shown, France, Germany, and so on. What is startling to me is what the United Nations considers the minimum amount of water that a human being needs for their personal use. Turns out it's 5 gallons per day, right? That's for washing, eating, and drinking. Okay, the world's poor live on less than 2.5 gallons of water per day. So that is a dramatic, stark contrast to how much water we have access to and the infrastructure of getting that water versus people in other parts of the world. Pretty startling. In terms of water use, yeah, we've got this phenomenon here where we are, I think, significantly overpumping our aquifers. one of the sort of most widely documented impacts of overpumping is what happens when you do pump water out of an aquifer. What happens to the water table, whether it's in a confined or unconfined one? That water table goes down. We call that drawdown, right? It's kind of like, oh, I don't know. It's kind of like getting one of those In-N-Out burger milkshakes. Okay, nice thick milkshake, and you suck on the straw, and that milkshake kind of depresses around the base of the straw. That's exactly what happens in an aquifer when you overpump it. So in Texas, we have this groundwater law, which basically says the person with the biggest pump wins, and you can go in and pump water out. And very often, what that leads to are wells being stranded elsewhere, right? So that well can be stranded, and the water table is drawn down below that well, and that causes an enormous problem. So speaking of overpumping aquifers, let me just spend a few minutes talking about this massively important aquifer system that we have here. And this is the High Plains Aquifer, right? You may have heard of the High Plains Aquifer here. Some of you may have heard of it by another term called the Ogallala Aquifer. That actually just refers to a specific set of limestones. But what you're looking at in this map here is the geographic extent of the High Plains Aquifer. So this is a subsurface aquifer that stretches all the way from South Dakota, a little bit in Wyoming, a big core of it. The colors here represent how thick the saturation is. So over 1,000 feet of saturated rock in Nebraska. That's why they get so much of their water from groundwater, from that previous diagram. So it cuts across these 8 states, right? And into the panhandle of Texas. And there is the northern High Plains Aquifer, the middle High Plains, the southern High Plains. The southern High Plains Aquifer is really the one that is here in the panhandle of Texas, right? And if it wasn't for this aquifer, we wouldn't have agriculture out there, right? This aquifer, the discovery of the subsurface swimming pool, if you like, of water is what led to the Great Plow Under, and then the drought, and ultimately the Dust Bowl. But if it wasn't for this aquifer, we would not have agriculture in the panhandle, okay? About a third of all the crops in the US are irrigated from this aquifer. So there's the whole High Plains Aquifer in blue, and the estimates, and this is the kind of shocking estimate, I think, is that by 2060, almost 70% of this groundwater will be gone, right? We are chronically overpumping the High Plains Aquifer. And the people that are doing it know that they're doing it. But in order to keep their crops irrigated and their cows hydrated, they have to, right? So here are a couple of maps. I know this is kind of tricky because it's hard to show this in a slide, and I think maybe it produces better. It produces better in the book. But this is the take home of what's going on in the High Plains Aquifer. Okay, so what you're looking at here on the left-hand side is the change in water levels in the High Plains Aquifer. Anything in red means that the water level in that aquifer has gone down by more than 150 feet, okay? 150 feet during what they call the sort of development stage, right? So in other words, from commercial agriculture in the Midwest, right? So the browns, the oranges, the pinks, those are the areas that are of greatest concern. There's some small parts that have gone through a net gain, but you can see where the greatest concern is southwestern Kansas, the thin slither of the Oklahoma Panhandle, but the Texas Panhandle is where the greatest concern is, right? On the right, you're looking at the percent change. So anything in red here, the water level in that aquifer has gone down by more than 50% since farming really began there, right? So again, stretching not quite from El Paso, but stretching sort of, from it's west of Midland, right on the New Mexico border, up through Lubbock, up through Amarillo. We've got parts of that aquifer that have declined by more than 50%, right? And that's why the estimates are that this aquifer is going to begin to dry up by the middle of the century. Guys, I don't think there's any doubt when you look at what's going on here that the landscape in West Texas is going to change dramatically in the next 20 to 50 years as they continue to overuse this aquifer to keep agriculture going through things like this, right? Center pivot irrigation. Yeah, it's catastrophic what's going on out there. You add to that potential climate change and another 2 to 3 degrees Celsius warming, and I think we're in real trouble, to be totally frank. Any thoughts or comments on that? Anybody from West Texas? I think someone is. Anybody from Midland, Odessa, Amarillo, Lubbock? Maybe, no? Okay. All right. Then just to wrap this up, one thing, I don't want to forget about this. This is an important environmental issue in coastal areas. This comes back to overpumping aquifers. But what happens along coastal regions is that as you start overpumping aquifers in coastal regions, we're seeing this all the way from Florida back to Texas, Louisiana, is that as you pump these aquifers in the coast, you start not only drawing down the surface water, but you start pulling in the brackish water and the salt water. That's known as saltwater intrusion. And once salt water gets into a well there, you're in real trouble. You're pretty much in tow. And then the final topic that I just want to mention, right, is this topic of virtual water. This is often overlooked, I think, when we talk about the sort of so-called water crisis. And virtual water is hidden water, right? This is the water that we use in everyday items, okay? So for example, if you just look at beef on the left-hand side there, right? It takes about 4,000 gallons per kilogram of beef, of water, okay? Because, you know, the cows have to drink, then you've got to grow the crops and grow the foods and everything. So hidden or virtual water in everyday items is just an important part of the conversation that we have in terms of sustainability of water. And there's quite a few apps out there. They're pretty cool if you're concerned about your water footprint, as we all should be. You can do your shopping with this app and it'll tell you kind of what that hidden water is. Okay, so the final slide this morning then is, you know, the crisis is here. I think that there's a strong argument that the next war, and some would argue that we are already fighting the water wars, right? People are in the Middle East are arguing over water rights. People are buying up water rights from Texas all the way to California. I'll show you some photographs tomorrow of lakes and reservoirs in California. It's serious, is what it comes down to. I think we don't feel it necessarily here, perhaps in Texas, because I've yet to turn on the faucet without getting water. There have been water restrictions in terms of watering lawns and so on, but we seem to, I don't know how you folks feel, but we seem to have this sort of perception that we've got plenty of this stuff and that we're not going to run out anytime soon. And I think that is perhaps a bit of a misnomer depending on where you're from. So thoughts, comments, or questions, everybody? I'm gonna end a little early today rather than begin the water pollution stuff and mix that up halfway through. So anything on water resources? Comments, thoughts, questions? All good. If I can fix my computer mouse. Okay. All right. So let's end there, and we'll end a little early today. And then tomorrow we're going to do water quality. Then we will come back and wrap everything up.